the Per Hellender Empire from IBP Greifswald. And this is the first of 2 talks that he will give. If you like what you see today, come back tomorrow, next week. And this is about global particle and cell simulations.
Yeah. Thank you. So I'm sorry for this technical prelude. So, global particle and cell simulations of Alfvenic modes. Okay. It's interesting. Okay, takes time. We know, of course, that there are fast particles in magnetic confinement device, either fusion-born or produced by neutral beam injections or IC-rate heating with different energies. And if characteristic timescales of those fast particles, like transit frequency or some precession drift frequencies, coincide with, for example, toroidal Alfvenic eigenmode frequency, then an effective resonance interaction can occur, and the wave will be destabilized, corresponding waves will be destabilized. The bad news about it is that one gets associated outward transport of particles with all unpleasant effects like non-even heat load, and good news, one can possibly use those instabilities for the diagnostic, so-called MHD spectroscopy, like measuring the safety factor profile details. And there is also an idea of so-called alpha particle channeling, which is a direct transfer of the fusion alpha energy to the bulk ions through these unstable Alfvenic modes. So these modes they deserve to be studied. There are many approaches to this study, and traditional numerical approach is using the so-called hybrid MHD scheme, which is a combination of MHD treatment of Alfvenic instabilities with a kinetic treatment of fast particle species. This approach may be effective in terms of computational time, but it has drawback because it doesn't treat accurately the various bulk plasma stabilization mechanism, radiative damping, Landau damping, etc. So the better choice in terms of physics is the gyrokinetic approach. There are now few groups working in this area, and okay, so this is what we use, and these are the equations which we solve. This is a linearized Vlasov equation. We don't have collisions in our approach so far. The gyrocenter equations of motion in so-called p-parallel formulations with all familiar drifts like E equals B, magnetic drift, so on. And of course, these are Gyrovich potentials, how the field enters those equations. So the usual system, gyrokinetic system of equation. Yeah, please.
So in your formulation, you don't allow for magnetic compressibility at this stage?
Yeah, that's right. That's right. It's reduced to MHD. Okay. I mean, the equivalent there would be reduced to MHD. So the system is closed as usually by the gyrokinetic quasi-neutrality equation and parallel Ampere's law in this case, without compressible effects, without a perpendicular perturbation. Again, p-parallel formulation is used for that. And well, this is the usual stuff. The polarization density is written in the so-called long wavelength approximation. This is not mandatory. We can also use sort of exact expression if you want to study some radiative damping effects. Okay. Radiative damping effects, FLR effects on the mode stability. There is a claim that form of the polarization density is important for radiative damping features. And we can do it as well, so this is not mandatory. So the numerical approach is particle and cell method. This is some technical details of this method, like discretization of field equations with B-splines, Fourier transform in the direction of symmetry. The problem which is to be solved when one does electromagnetic simulations with a particle and cell approach, treating all species kinetically, also electrons, because there are approaches which treat electron in fluid approximation, and bulk ions and fast particle ions, fast ions, energetic ions are treated kinetically. So here we treat everything kinetically, also electrons. And then so-called cancellation problem appears. It is relatively severe. It must be solved. It can be solved, and this is one citation. So far you have it. You can perform electromagnetic simulations. We cared about performance optimization, as everybody does. So we have nice weak scaling features. Okay, so now about physics.
Just to be clear, this is non-axisymmetric and global, or
This is axisymmetric and global.
axis?
That's tokamak global and linear. So,
They allow you to do tokamaks and GraphSmart?
otherwise I would not come. Would not be allowed to come here, perhaps. I don't know.
Oh, no, we allowed parallel.
Yeah, all right.
Just a practice problem.
Now, tokamak
I
is
see.
the point is that tokamak is a zero
It's a
approximation.
quasi-symmetric stellarator, yeah.
No. Tokamak is a zero approximation to the stellarator. If you think of simplest possible stellarator, this is a tokamak. So perhaps we need to study this, as a toy model. This is our toy model.
I myself much prefer a cylinder as a zeroth approximation to the tokamak.
Yeah, okay.
It's the zero top.
Yeah, it's a summation to
The cylinder, yeah.
Yeah, so this is an example which we study. This is light aspect ratio tokamak with circular cross sections. The aspect ratio is 10. We choose relatively strong magnetic field. This is important to make the widths of fast particle orbits reasonable, not larger than the system size. We choose relatively small bulk plasma beta. The reason for that is to reduce coupling of the Alfvenic waves to the sound waves with all associated effects like frequency shifting and so on, appearance of BAEs. And we choose the flat bulk plasma temperatures and densities in order to avoid things like drifted stabilities, for example. Toroidal mode number is 6. The safety factor profile is here. You see that this is, it is chosen like that in order to have a clean situation with only one gap present. One gap in the shear Alfvenic continuum, one toroidal Alfvenic eigenmode expected for the poloidal modes. The mode numbers 10 and 11, toroidal mode number 6. Safety factor in this position, in that position, is 1.75. So it's a clean situation, model clean situation. Indeed, in our simulations we have found a mode with a frequency red solid line, and we compared this frequency with reduced MHD calculations and found this dotted line, and we see that those frequencies coincide nicely with each other. So this is a toroidal Alfvenic eigenmode which we have found in our gyrokinetic simulations.
When you say MHD, you just mean
I just mean benchmark.
MHD, you would simulate the MHD equations in the torus.
The reduced MHD model.
Reduced MHD.
Yes, which is solved eigenvalue problem. So
And that's the real frequency, not the growth.
that's a real frequency. That's right. Coincides nicely. Okay, so this is the time signal, how the time signal looks, which we get out of the simulations. This is again toroidal Alfvenic eigenmodes. I have plotted here just two dominant harmonics, 10 and 11. And you see that they are really, for example, for phi, they are really in phase, and the amplitude is very much similar, so like it should be. And for A parallel, they are in counter phase, and one can show that this property is associated with small E parallel, which should vanish in ideal MHD approximation. It is not vanishing here, it is finite here, but it is small, and this is a reflection of it. Yeah, and perhaps you can see that the signal is a bit more complicated than just harmonic decaying oscillations, and it indicates that we have also additional components here, not just toroidal Alfvenic eigenmode, but perhaps for sure also kinetic toroidal Alfvenic eigenmodes.
Why is the amplitude not growing in time?
because we don't have fast particles, for example.
Oh, this is just the image.
Yes, this is the first, the background, so to say. We start from no fast particles, just let's look for toroidal alpha eigenmode.
And you
Kinetic.
initialize with what?
Pardon?
What do you initialize with?
Okay. It's important, of course. I take initial signal has two poloidal modes, 10 and 11, which I expect to couple for these parameters. I initialize them with a Gaussian in a radial variable centered in the position of the gap. The velocity distribution is Maxwellian for the initial perturbation. So I put some energy, of course, into the system, and then I let this energy to decay, and this is the dominant way of this decay, but not the single one, of course. There are also kinetic toroidal alpha eigenmode contributions.
Alexey, so you've got a decaying TAE here.
Yeah,
Do
yeah.
you match the analytic predictions for the decay rate from, for example, continuum damping, or is this? What's the main damping mechanism in your code for this?
In this particular case, I suppose this is iron-Landau damping and radiative damping. It should be more important, even more important.
Yeah, that's continuum damping, right? Yeah.
No, that's not the same. Continuum damping is when you cross the continuum, and I have chosen
You've chosen
everything in such a way that I do not cross the continuum.
Okay, you're just coming
It's just radiative damping to the wall.
Well, as I understand it, I just yeah.
Must go somewhere.
It's not radiative damping. Okay, where it goes. It's sort of leak of energy from the gap to the continuum. This is how I understand it. So coupling to kinetic toroidal alpha eigenmodes, for example, and this is how energy is gone from the main toroidal alpha eigenmode outside. So it's coupling between different perturbations through FLR effects. This is my understanding for what happens, and I know that this is important. I know if I play with ion temperature, with bulk ion temperature, I can see it really nicely. Not in this system. This is very simple system, simplified. So in more realistic systems, there are very clear signs. So I can see this radiative damping really clearly with scalings and tendencies. Okay, so further.
Does that impact the resolution you need? Because presumably that's coupling to extremely fine scale structures.
So
Or is it
in this,
pretty much safe to the grid scale?
I do not see these extremely fine scale structures in this particular case. This is large aspect ratio. If I have smaller realistic aspect ratio, like 3, like jet, I think 3, something like 3, then it's those structures are more pronounced. So I get all this. I can show. I have not in the talk, but I have the pictures here. Yeah, this is a mod structure. This is how it looks like. It doesn't have all this fancy, you know what I mean, this FLR things. But this is related to the aspect ratio. It's large. Well, this has a form of toroidal alpha eigenmode, 2 dominant harmonics, and this is particle and cell simulation. So this is evolving signal. I measured at some particular point of time, but this is a typical what I see coming out of the simulation are different. Well, so far the mode evolves.
Have you chosen to use near-line following coordinates?
Now in this case, so far I have circular cross section. I use just very naive definition for the poloidal angle. It's not for the line following. It's.
So along in the toroidal direction, you have many grid points.
I don't have grid points in toroidal direction because this is an axisymmetric system and linear simulations. I don't need them.
Nice.
But
It's just completely spectral.
sorry.
It's spectral and everything but radius.
In toroidal directions, Fourier transform, and I keep just one toroidal harmonic, so I don't need this resolution. But I think field line feature is becoming important. So far, I have shaped plasmas. Filtering, at least, for filtering, it is important. So far we have found this stable toroidal alpha eigenmode. We want to consider what happens if we use fast particles, add fast particles, and we choose a flat fast energetic and temperature profile, and this sort of energetic particle density profile. The distribution is chosen to be Maxwellian. the maximal gradient of the density of the energetic particle density coincides with the position of the gap. So this is a setup, and we expect this mode to become unstable. Indeed, this is what happens. This mode becomes unstable. What we do here, we study how the mode changes when the fast particle density increases. And this is the frequency, this is the growth rate. Here, initially, at small fast particle density, the mode is stable, then it becomes unstable, and the scales here are logarithmic. So this is in linear scales, I suppose, would be a straight line. And well, yes, it grows, of course, with the fast particle beta fast particle density. The blue line here is what results from the hybrid MHD calculations, pretty much the same as would result from the theory. And one sees that the growth rate is overestimated in those MHD in those hybrid theories or simulations. And this is related to the bulk plasma effect, to the radiative damping, Landau damping, etc. Finite orbit width effects, finite Lamor radius effects, as we will see in the following transparencies. So here I plot the gap and continuum. This is where the boundaries of the gap in the frequency. And we see that the frequency also increases with the fast particle beta and leaves at some point the gap and enters the continuum. One can say that we see non-perturbative energetic particle mode, so far it lives in the continuum and not in the gap. Perhaps this is correct, but there is also another effect which is interesting and needs to be studied. We know that so far we have acoustic Alfvenic coupling. Then there is a upshift of the continuum, of the shear Alfvenic continuum. So this
I
is.
missed what FOW is.
No, it's not FOW. No. It's MHD. You have MHD picture. So I consider now the frequency. The frequency.
What is FOW?
Pardon?
What is FOW?
What is it?
What
What does it mean?
Finite orbit width effect. Do I have it here or it's
Finite orbit width. Okay.
Did I?
No, it's on the last line.
Yeah, this is why this thing is larger. What is neglected there in the local theory.
And you've got all the FLR in your
Sure.
calculation, including in quasi-neutrality.
Including polarization density, the same.
Yeah.
In this particular case, no. But I made studies. Not for these pictures, but for this setup. I made studies. And the difference is not as large as one would expect. Small. And I can show those pictures. I have them, but not in the dock. I have them on the computer.
But if
You're sort of keeping FLR in one place and not in another place. So it's a little inconsistent.
It's a little inconsistent, but this is a little traditional. I mean, everybody does this thing. In the polarization density, of course, you do.
Traditional doesn't mean it's not wrong.
Let's say.
What's the problem? Why
For the
not?
non-experts, why don't
Why not?
people do it?
Well, it's technical reason. First of all, polarization density itself is a FLR effect, right?
We could get into a long discussion on that.
Yeah, whatever. Whatever. You have
They
this
don't
one.
care what we call it.
You have this 1 minus gamma 0, for example, in Fourier space.
Yeah.
If you expand it to second order and k perpendicular, then you get Laplacian in a real space.
Yeah.
If you solve equation for you get Poisson equation.
Yes?
You solve Poisson equation in a real space, and this is differential equation. This is one thing. If you don't do that, you get an integral equation. You can solve this equation as well, but there are some technical modifications with matrix and so on. So this is not the simplest setup one can have.
When you
But-
compute the averages in the kinetic terms,
Yeah.
you have to include the average round a ring. How do you compute those?
Oh, it's a normal particle and cell procedure. Very straightforward particle and cell procedure.
I know what I think the normal procedure is. I want to know what you did.
4 points, 8 points, everything.
In this case, 4 points.
In this case, it might be 8. So we have adaptive everything. It depends on mu, for example.
Right.
Could I just, and this
Sorry,
is,
just
but-
complete the answer to your question.
Yeah.
It's because it takes too long to do the more generalized Poisson equation.
No, it doesn't take too long. It's a bit more complicated, and this is the first thing we wanted to do. This one. We just have chosen the simplest setup possible, and long wavelength approximation is what routinely used in all particle and cell codes. So far, you are not Fourier. You are not doing spectral method. You use long wavelength approximation. This is not mandatory. There is a way to circumvent it. But we just were on a traditional standard level. If you like, I can show you. I have some pictures.
could I just ask you, what's given this approximation?
Yeah.
What is, in doing this study, what are you after? I mean, what's actually important to you? Is for example, how that TAE becomes, I don't know, a kinetic Alfvenic wave at small scales or something like this? Is that going to be important to you or not? Is anything small scale? Is anything K rho I or the U?
Gets lost. Oh, this is what you say.
Yeah. Is how energy going to get lost going to be important to you in this study?
So for those simulations, it doesn't seem to be of large importance. So for you increase K perpendicular rho I or rho energetic particles, of course. By the way, for polarization density, we here in the regime where K perpendicular rho I is not so large, it's not so huge. The polarization density approximation, long wavelength approximation, is accurate here. For energetic ions, it is not accurate. Of course, the energetic ion gyro radius is big, but the contribution of energetic ions into the polarization density is negligible because of it's 1% of the total density or less, depending on the parameter chosen. So this approximation doesn't really make
I think I'm asking
lot of
less of an
impact.
approximation question than a sort of a motivation question. What do you actually want to find out as a result of all this? You just want to check that there is a TAE, or do you want to find something out about
unstable TAE? It's a very basic, very simple question.
Do you want to find out anything about it for which FLR is likely to be important?
I do have FLR.
Well,
And you know, we must distinguish between FLR for energetic particle ions and FLR for bulk ions and how important they are.
Well, you just say, you say everything is long wavelength, so maybe you don't need any FLR at all. I mean, why?
I do need FLR, and I will show you. So first of all, this blue line, shows you explicitly that I do need FLR. Okay, it's not complete proof because there are other things involved as well. I have some pictures following which show you more. Well,
but this code
clearly.
CAS3DK is a hybrid MHD.
This is hybrid MHD.
Does it have FLR for the energetic particles?
It doesn't have FLRs at all, so it neglects it.
Neither energetic.
Yes. Of course, this is not. I understand that this is important. I will show that I see importance of this effect.
Oh, I see. So you're saying if you add some FLR, you move from the blue line to the red line.
I do not add some. I add most of FLR.
Right.
I would claim 99%.
So you also said earlier in this polarization density discussion that John always wanted to have that you've checked that if you put all of the FLR, it's not that different.
It's a bit.
So how different is it? Is it less different than blue line is from the red line?
Yeah, definitely.
How did you do it? That's hard. In a global code.
How do I include polarization density exactly?
Yeah,
Is that the question?
that's hard.
Okay, we have a word for that. It's called generalized solver. This is not that hard. This is just you get integral equation instead of differential one, and you need to construct this matrix, take an integral over the phase space. So we do it as a particle and cell codes. We just apply charge assignment once to compute the polarization density matrix with all techniques. Am I clear? So just make additional charge assignment, sort of charge assignment, constructing not a vector but a matrix at the initial step. And we include all the orbit averages, and we can use like 40 gyro points instead of 4. So all this flexibility is there. But of course you pay for that. The matrix it depends. But if you have K per pro I large, and you have tokamak, and you have realistic tokamak, the matrix becomes huge, really huge. But not in this case. This case is harmless. Yeah, and okay, so the frequency grows with a fast particle beta, and I think it has MHD background, just acoustic effect. So this is how the eigenmode looks like from here. It's bright, white, big. It's compared with a stable toroidal alpha eigenmode. Well, it has certain poloidal mode structure. Again, 10 and 11 are dominant, at least clearly for phi, but well, and it is centered more or less around the gap position, slightly shifted, but a little bit. Okay. So this is the next sort of sweep scan we are doing, parameter scan we are doing. Here the fast particle beta is kept constant and comparable, slightly less than the bulk plasma beta. And we change the fast particle temperature. And of course we must change also fast particle density in order to keep the fast particle beta constant. So again, the frequency, the growth rate, gap, continuum, and here we get in this regime, in this part for larger betas, we get unstable toroidal alpha eigenmode. This mode lives in the gap and it hardly changes with the temperature because beta is constant and this image defect is absent here. There is no this upshift. Here, this mode lives in the continuum, and I would argue that this is truly non-perturbative energetic particle mode. We have smaller temperature, which means we need larger densities, fast particle densities. This is non-perturbative here. On the growth rate picture, we see a resonance. This resonance is centered nicely around thermal velocity. Thermal fast particle velocity is around 1/3 of the alpha velocity, as one would expect. And we see that the growth rate goes down, becomes smaller at larger fast particle temperatures, and this would be fine at orbit width stabilization, because orbit width, of course, increases with the temperature.
Is there some physics significance to the fact that you quote beta F for 3 significant decimal places?
1, 2, 3?
Yeah.
It's my comforting me. This is.
But why?
It's 1, 3, 4. It's
Why
a
so
beautiful
accurate?
number.
I mean, is there
Not
some
that accurate, John?
Well, it's no, it's just psychological sort of. I don't know. Comforts me somehow.
it's not some result of some theoretical formula or something.
It's
There's
okay.
some threshold value.
It's okay. No, not intended at least.
This way, John, if you redo the calculation, you'll be able to compare it.
When? No, not if. When?
I'm sorry, go ahead.
Yeah, this is how the unstable toroidal alpha eigenmode looks like from this region, and again compared with the stable TAE. Well, it's a bit wider, but this is TAE. I mean, it looks like TAE should look, with dominant poloidal modes nicely coupled to each other, shifted a little bit radially, so as it should be. And now this region. This is how it looks like. The energetic particle mode versus stable TAE is shifted. It's really shifted, and it has just one dominant poloidal harmonic. The initialization was the same here and there, so I initialize always according to the same scheme. So this is EPM, energetic particle mode, for the parameters.
And so that dominant M is the one that corresponds to the continuum at that
Yeah,
point.
I will show. I think I show answer next transparency. So this is perhaps the answer. M equal 10, the dominant M. This is where it is located, and this is more or less the frequency which I measure for the mode. So here, the frequency which I measure in the simulations, and location, center, which I see, and mode number. So it corresponds to the resonance with the continuum of the mode, determined by continuum properties. This is next parameter scan. Again, we change the fast particle temperature, but now keep the fast particle density fixed, which means that, yes, it means that the fast particle beta is increasing. Omega, gamma, continuum, gap boundaries, and you see that omega changes, and at larger fast particle density it increases and approaches continuum boundaries. And I would assume that again this is related to this MHD-like effect associated with increasing fast particle beta, this upshift. This is the growth rate, and here comes this FLR, FOW story, so finite Lama, finite energetic gyro radius, finite energetic particle gyro radius, and finite energetic particle orbit with its effects. 3 lines. This line corresponds to the particle and cell simulations, including all energetic particle FLRs and FOWs, finite orbit with effects. This is a red line. The blue line corresponds to the particle and cell simulations without energetic particle FLRs, and the black line corresponds to hybrid MHD simulations, which have neither FLRs nor FOWs. And we see that first of all, we see quite a difference between the blue line and the red line coming from FLRs, energetic particle FLRs. It's important to care about energetic particle FLRs. Then we see that the blue line coincides nicely with the black one, with the hybrid MHD, at smaller temperatures. At smaller temperatures, there is no FOWs, finite orbit width effects, for energetic particles are relatively not so big, and this is why it coincides so nicely up to a certain point. And then there is discrepancy, relatively large discrepancy, and this is caused by orbit widths of the energetic particle. They stabilize, clearly stabilize the toroidal alpha eigenmode. Yeah. Yeah. Okay. Summary. We see that fast particle destabilization of the toroidal alpha eigenmode and its modification into the energetic particle mode can be modeled with global particle and cell code. Yeah, we have seen some nice, interesting, consistent effects. And as a next step, this is the next step 1 year ago. So here we are doing something, benchmarking as usually. This I have done already. So numerical equilibrium are working, and small aspect ratio also one can compute them with realistic safety factor profiles with many gaps, with sound effects included. It's interesting because, for example, one of the things one can see, so these were destabilization of the toroidal alpha eigenmodes by the fast particles. If you go into realistic situation and choose the bulk plasma beta not too small, realistic, then you can get ballooning modes, kinetic ballooning modes, perhaps ballooning modes, and you can see stabilization of those. I have a picture, so if there is interest, I can show stabilization of those modes caused by the fast particles. Yeah, and this is sort of things one can do. Alpha sound couplings is especially interesting, and well, this is what gyrokinetic codes should do. King microtuning mode, here the electron inertia should be really of importance on the resonant flux surfaces. This is what I think. And then electron fluid model is not so good, perhaps, because it neglects inertia effects, electron inertia effects. Nonlinear effects, there are many groups interested in that. This is what we must do. So far we are doing stellarator theory, because if we're not doing that, nobody else will do it. Maybe not an episode. Yeah, that's all. Thank you.